talk about a little bit more calibration. You certainly referred to calibration number of points. This is just to fill in maybe some of the gaps that we might have jumped over. And this is your typical traceability pyramid, nothing earth-shattering here, but you've got your industrial measurement at the bottom. Working your way up, you've got some secondary laboratory standard that you're calibrating against. That gets calibrated against your primary standards, traceable somehow to a National Metrology Institute, and ultimately SI units. So it's always a good thing when you're planning a temperature calibration process. You ask yourself, what goals do I need to achieve? We recently we got ourselves into an interesting problem. We developed this new thermometer that we had with the Bluetooth in it that I was showing you that we're using here, and when we came up with the new thermometer, it was more accurate than our calibrators. So now we had to develop new calibrators. Then we found out that our lab didn't have the capability to calibrate the calibrators, and I mean, as we were doing this planning, so we actually had to go back to A2LA and develop, we developed new methodologies, and we went and got a new audit and improved our scope, but it was quite a bit of effort. It was more effort actually to develop the calibration process for our new calibrator than it was to develop the product. That was, we didn't anticipate it being that difficult. And we'll look at, I'll tell you a little bit about what we did here. So you know, again, your goals, what are you trying to accomplish? How accurate do you need to be? You always need to know that first. And what is the impact? You know, it's like any good ISO 17025 process. What is the impact of you know, a certain level of accuracy? Do people get sick? Do people get endangered? What happens to the impact on the general public? So that's what you have to spend some time thinking about before you can figure out, well, how much and what's the budget that I can spend to achieve that level of accuracy. It's always a circular process. So when you're calibrating temperature, though, you really have you have three areas, three methods. So one is in the millivolt domain. So you can, when you're calibrating both, say, thermocouples or RTDs and instrumentation, you can operate in basically the millivolt area. So you can get millivolt sources and really precision voltmeters, 8.5 digit DMMs. I think Fluke has a new one that they'll be showing out here on the show floor this week. I think it's the 8588. Of course, the 8508's one people used a lot, 3458. There are a lot of like WaveTechs that are still out there. Transmil makes one. But those are available, and you can operate in, so you can measure a thermocouple, you can measure its absolute millivolt behavior, and then you can compare that to tables. Or you can operate in the temperature domain, and there you have a reference thermometer that you're using, and so some of these conversions are done obviously in these devices. You can also use physical standards, which are really, really quite expensive. Physical standards, these are basic freezing and boiling points of water and other substances that you then use to fix some known temperature points. This is called you've heard this term, the triple point of various substances. And the triple point is the place where a substance is in equilibrium between a solid, liquid, and a gas phase. And it's hard to achieve. And where you can tell that is if you think about the heat transfer, if something's evaporating, well, it's removing heat from the system. And if something's freezing, heat is also transferring from the fluid to the ice. And if the ice is melting, you're transferring heat, you're liberating heat from the ice to the fluid. So that's when you build that ice bath that we did. It's very little fluid. You want it to be sort of balanced on that equilibrium point. And of course, how that happens matters not only to the various substances that you can choose, but then also the purity of the substances. So we did an ice bath, boiling water, easy to maintain, cryogenic gas boiling standards. You try to do hydrogen, nitrogen, whatever these things. These are hard to deal with, or high temperature ones are also. So you've got molten lead, zinc, and silver freezing points. Freezing points are always better than boiling points because they're not really susceptible to the changes in barometric pressure. We're going to look at that just as a little object lesson. Excuse me. So ITS 90 International Temperature Scale, we've talked about this a few times, good referencing. It defines the temperature scale. One of the points that Richard made is that an SPRT was used to really define that whole scale. The point is this is anchored by 13 reproducible physical standards from the triple point hydrogen at 13.8 K to the freezing point of copper at 1337.77 K. And the thing to note here is that the purity of these substances really matters, because when you're trying to get something to this level of accuracy, you can't have, if you alloy, if it's some silver or tin and it has some other material in it, it's now you've changed the material. So its triple point has changed slightly. So maintaining the purity of these baths is a huge problem. And here's some of the higher temperature ones. So the freezing point of tin, the freezing point of zinc, and the freezing point of silver. The boiling point of water is very popular to use. It's like, oh, I'm going to check my probe, because you can say, oh, I'm going to use it at freeze. I can make an ice bath easy enough, and then I can make I'll boil some water, and I'll check 100 degrees C. So it's a problem. And here's something you have to actually be aware of. This is a table of the boiling point of water at altitude. So, 500 foot, 99, you've already lost a half a degree. We had somebody call in and say, your probes are all wrong. It's like they're reading, they're reading 5 degrees off. I was like, well, where are you? I'm in Denver. It's like, well, I said, no, they're right. They're perfect. Okay. So, and the point is, it's not altitude related, right? It's really pressure. So it's 100 degrees at 1 atmosphere of pressure, which is theoretically pretty much what you get at sea level. But of course, if you have anybody who watches the weather, the pressure does actually change even at sea level. And it's not linear either. It's a nonlinear equation. Of course, where we're dealing with is in this small region here. Excuse me, not that region, we're going this way. So, it's pretty linear within the region that we're doing. So let's just play a little game here. So I use distilled water. Oh, so that's something else too, is when you're making a boiling standard, a gram of sugar in a liter of water raises the boiling temperature a half a degree C. So that's a fun thing to do. So I've got my water slightly boiling here just right. So what are we saying? We've calibrated this probe already. So I'm reading 99. See, I'm reading 98.5. I think that's a local radio station. Actually, now that I took the lid off this thing, classic problem. I just took the lid off and the temperature, I've evaporated enough water off the surface. I changed this thing. I first put it in. Let me do it this way. Keep the lid on so it keeps boiling. Yeah. There we go. illustrates the difficulty. So I'm having trouble getting this consistent temperature. We get about 98.3 is what I'm going to call it. So let's go back to the table here. What altitude are we? Anybody know? From this chart, what would you guess? If I said it was, 98, let's say 98.5.
1,000 feet, but we're not 1,000 feet.
No, we're actually 650 feet. So, what's wrong with my experiment? We calibrated the probe. This is the probe that Richard had zeroed before, so that's good. The water is actually boiling. The water's distilled. Well, certainly, as soon as I take the lid off, the temperature drops. It's a difficult thing to achieve accurately. Let's do it this way. Let's throw let's throw this one in here. Then I can leave the lid on. See what we get there. So now it's reading, I'm not going to hook this up, but now it's reading exactly 100. Problem is it's varying. Here's a good example of my experiment. I can see if I watch this thing, you can see it go up, and you can see as the hot plate shuts off and the heat goes down. So my problem here is a control system. Boiling standards are difficult to maintain. They don't like to do that very well. Let's find out what the IR gun says the temperature is. That's pretty good. It says 95, 92. It's varying between 92 and 95 degrees. So it's not too bad at about 100. But as we saw, when you got up to 200 degrees, it became very nonlinear very quickly. So anyway. That's what happens when you try to make a boiling point. How are we doing time-wise? All right. So calibration. Talk a little bit more in depth about calibration. You got dry block calibrators. We talked about circulating bath calibrators. Here's what some of these look like. Here's a tell true basic calibrator. So you've got a cavity here. You put your probe in. There are some that are heat and cool models, so you can do different temperatures. This is always a pain, of course, because whenever you change the temperature, you got to wait a long time. And there's also ice point references. So if you're really just trying to zero probes, you can have something, instead of having to fool around with crushed ice and make a bath, you can use an ice point reference. And the best accuracy you can get is about 0.1 C. You can get, half a degree C or 1 degree C cheaper instrumentation, but about the best you're going to get out of something like this is about 1/10 of a degree C. When you want to get more accuracy, then you go to a circulating bath. And the way a lot of people use circulating baths, they use DI water or silicon oil. Various temperature ranges you can get from -100 to 700 C. Obviously, this is not water, and neither is this. This is a high temperature oil or an oil, because the water's going to freeze there. And you can find some baths that'll almost control to within 25 millik. But the key for most baths is not the accuracy of the control system. What you want is stability. So it's how stable the bath is, because you're going to discipline it with an external sensor. When we upgraded our lab's accuracy, we bought a bath, and it had pretty decent stability, but we use an SPRT to bring it down in uncertainty, and we got actually down to with our own SPRT and external, really external long scale voltmeter. That's a temperature scanner. We could get to 6 millik, which is actually pretty decent. And we're using that to pattern some of our own RTDs and sensors that we're putting into products. So on this new calibrator that we have, we wanted to improve the cold junction performance of it. So we had to pattern the sensor that we use for measuring the cold junction. And what we found, though, we started off, we wanted to do that right at around, room temperature. The operating range of that device goes from minus 20 to 55 C. So we didn't need something special. So we went with DI water. And what happened is the water affected the encapsulant on the RTD that we were using. So the RTD now is changing. Every time we used it, we couldn't come up with consistent results with the RTD. So we actually had to go to a silicon oil for that. So we found some interaction between the bath medium and the sensor itself that we were trying to calibrate. That was, like I said, that was developing the calibration system for the product was harder than developing the product. Also, when you're using baths, they don't, obviously you got a lot of fluid to change, so they don't typically, you don't change the temperature often. What you'll do is if you need to measure several points, you'll have as many baths as you need points, and then you'll be able to take your sensor or your instrument, if you're doing both, together all the way through that range. So these are both examples. The dry blocks and the circulating bath are examples of, sourcing and measuring temperature directly. Another way to do that is in the millivolt domain. Again, we mentioned this, and that could be with a long scale DMM or a temperature calibrator. And now this is more about calibrating instrumentation, but you could also use these for patterning probes as well. So, but if you do that with this, here's a 3458. If you're using a 3458, you're going to read millivolts, and you're going to have to do the corrections manually or use some software to do that from the tables. If you're using a calibrator now, you could use a benchtop or a portable. So a benchtop calibrator like this, Fluke 7526, that's actually an old Martel product that Fluke still makes, but that's kind of a dedicated temperature calibrator. It's pretty nice. It's meant for use in a lab. You get about 1/10 of a degree accuracy. And a portable, this is our new one that I know a lot about, so I'm going to use that and reference that later. But the portable one has about 2/10 of a degree accuracy. And the real difference is how well you can measure the cold junction. On an instrument like this, you can actually set that up with, you've got power coming out of the wall. You can actually create your own sort of isothermic area with a heater and keep something right at ovenize it right to a certain temperature. I don't know if Fluke does that. I'm just saying that's when you've got a benchtop calibrator that you're putting in a lab, you can do a lot of things to get it. And the interesting thing about that is if you do spend a whole lot of money, you can lower the uncertainty a little bit. And these are, excuse me, I use the term accuracy here. That is actually the uncertainty. K = 2, uncertainty of those devices. So when you're setting up a lab and you're trying to maintain some higher order accuracy, what are you typically doing? You're typically going to be using an SPRT. That's what you're going to be doing in the lab. If you're going crazy and you really need high level, you're going to have multiple triple point cells. And again, this is very expensive. You're investing, to really maintain this, you're investing tens of thousands of dollars. and repeated maintenance of those cells over the years. So you really need that, you're really going to need that extra accuracy to justify that expense. But you know, this is what primary standards labs are going to do. Or if you're a large company, Fluke maintains a whole series of triple point cells. Precision resistance bridges. Instead of using like a 3458, they're like MI. They'll be here at the show. Or what's the other company? MI and one of them slips on. Guildline, yeah, thank you. They'll make a precision resistance bridge. Some of these are AC bridges too. I talked about that thermoelectric effect. They'll use bipolar excitation. But another thing, when you get to this level, you're going to use dual currents. So you'll measure a temperature and you'll pass a certain current through the SPRT, and then you lower that current or raise it, either way, but you'll change it by a known amount. And so that what that allows you to do is plot the zero power point. Because when you're passing current through it, remember, you're heating the RTD to some amount. And so to subtract that out, if you do it at two different current levels, you can plot on a curve, oh, here's where zero would actually be if I wasn't messing with my sensor by passing current through it. So these are things that you consider when you're trying to get down to this, the best NMI practices get you to about 1 milli-K if you really got to get down there, but that's probably better than most people need to be. So this part of the presentation, slightly more commercial. I'm going to apologize for that. I'm using our calibrator as an example because it's the one I know. So we can explain some ways that you can use it for field calibration and also as a diagnostic tool. So not only can you use a calibrator to, sometimes you want to monitor your measurement circuit, but you're also sometimes monitoring a control circuit. So if you've got something that's keeping, a freezer that's keeping something cold or a heating system that's keeping something warm, you can use a calibrator to actually watch the process and see whether it's overshooting, how it's maintaining over time. You can also use a data collection thermometer for some of that as well. So one of the things that what's useful about a calibrator is with simultaneous source and measure, you can, on the display, source the temperature, but you can also watch a temperature input. And that's useful in a number of ways where you're monitoring a process. This could be, you could put your calibrator in the loop and you can see what is the signal coming in and then feed that out of the output. Or you could simply you could use this as a reference thermometer. You're simulating a temperature and then you're watching with your control system how it's responding with another input sensor. So if you're working in some industrial area, this is a very common application, and a lot of companies do this. So you have a simulation output. This is the source output. You basically set it up for, this is type K, and this is a type K transducer. Then you can simulate a certain temperature range, and then you can see how the transducer responds. So this is one way of covering some of those wider ranges with your instrumentation without having to actually create a temperature source that's 1,000 degrees. You can simulate that. And this is basically using the ITS 90 tables. They're built into the instrument. You key in a temperature and it replicates that out of the source based on the thermocouple you've chosen. The other thing you can do with this, of course, is that this is typically hooked up to some of the control system. You can set this in these calibrators, not just ours, but many of them. You can put them in a stair-step mode, and it'll go through 10 steps. You can leave that on a transducer. You can go over to the control area and see how the whole system is responding. We have a distributed control system or whatever it's operating with, or even a panel meter somewhere, whatever you have. Here's Another way that calibration is done, this is in heat treating, so we do some work with people who are doing AMS 2750 heat treating for aerospace. So you've got a heat treating oven, this is a simplification of it, of course. You've got a controller here, and this is often a K sensor because of the high temperature operation, but then this sensor will be an N. I ignore this, that says K, that's not right, but this would typically be an N sensor because N tends to be more stable and exposed to higher temperatures. So using the thermometer in this case, the reference thermometer is what you're using, so using the thermometer input, and you're simply comparing this to the temperature that the controller is seeing. And of course, what are some of the problems with this? The pluses are you get to calibrate the whole system. An assumption you're making is that of course, the inside of the oven is isothermic. Is this measurement point differ much from that measurement point? And when you're doing heat treating studies, there's a thing called the uniformity test, where you're actually measuring the uniformity of this oven. So these will be patterned. They're different class ovens, based on how uniform they are. This is a simplification, but there might be multiple points at which you can sample a sensor to calibrate your control system. Then there's another thing that can be done. So you can insert your calibrator between the sensor and the controller. And if you know the offset of the sensor, you can put that into the controller or into the calibrator itself. So in AMS 2750, when you're doing this type of calibration, you actually have to manually calculate what the offset of the sensor is to come up with what's the correction factor for the actual the controller or the monitor itself, because you've got to isolate what's the inaccuracy of the sensor from the inaccuracy of the controller. So what this calibrator lets you do is you can key in, as Richard did when he zeroed the probe, you can put that offset right into this and set this up in what's called transfer mode. It'll pass the signal that it gets here back out the simulation port, but it'll correct it for the offset. So now you have a corrected thermocouple signal going to the controller, and you can then record your calibration without having the effects of that, having to manually calculate that offset. That's handy. Here's really a lot like calibrating a transducer, but instead of calibrating a transducer, you're calibrating a PLC, and that's just into a set of thermocouple inputs. This next slide I put in here just to talk about intrinsically safe a little bit. People do this all the time. You've got a intrinsically safe transducer here, and then you've got a 4 to 20 milliamp loop. But then, in this application, this is actually a no-no, because this calibrator is not intrinsically safe. You'd really need to have an intrinsically safe one to have it connected to this device, or this has to be kept completely out of the intrinsically safe area, and you have to run cable in or something. So here's my shamelessly most commercial slide of the entire presentation. I want to show you something. We'll have this set up in our booth this week, so if you're interested in temperature calibration, I suggest you come see this, because this is kind of cool. What this allows you to do, we have a new calibrator. We haven't actually released it yet. We're still finishing some software, but this is a Bluetooth calibrator. And what you can do is, through your phone, you can run the app, and you can actually run a sequence of points. It will talk to the calibrator, say, go to 500 degrees. This is the wired connection to whatever you're calibrating over here. If it happens to be one of our Bluetooth thermometers, it'll talk to this instrument, and you can automate the whole calibration process, and it'll email you back all the data. So it gives you the serial numbers, the data points, everything you calibrated, and that's back in your inbox, so you don't have to write anything down. You can go out in the field and do that. If this happens to not communicate, if it's just a regular transducer or thermometer of some sort, you can actually enter the numbers in on the phone, and then it'll still send it back to you and email it back. So that's what we're showing at the show this year. So that's fun. That just allows you to do a field calibration and automatically collect the calibration points, and they're waiting for you whenever you go back to work. So, yeah.
So if I had, let's say I'm running a long-term chamber, and it's, it's automatic set points where it goes to different ones and different stabilization times for hours on end. Could I put that on there and they would just leave it, go back to my lab and then leave it, and it would email me all the data over the
Yeah, it would.
day or two?
It would do that.
That's awesome. You can have a few of those, and you can do a whole factory after you set one day aside.
Right. Yeah, you just set it up and let it run. What is the limitation? Battery life.
Yeah.
And that's actually something that we spend our engineers spend a lot of time doing. So these will last 1,000 hours on three AAA batteries. Sorry. But this one will run 500 hours. The calibrator takes a little more power because you've got to simulate. You've got some other circuitry you got to deal with. But so it would last 500 hours in an application like that.
Like the chamber's probably 8 to 15 hours at most.
Yeah. There's some calibrators that really eat batteries. We didn't want to do that. We make fun of our competition with that, with some slides, but. One thing to look for when you're looking at calibrators too is many portable calibrators, because there's a number of them out there from different companies, but we talked about all those things that cause errors in a temperature measurement, and Tempco is a thing. Many of them specify their accuracy at 23C, but you have to take into account any change, any deviation from that 23C. It's part of the Tempco. So you really want something that's going to maybe operate over a wider range and still maintain the specifications. Or if not, you just have to take into account when you're especially when you're doing a field production work. You have to that goes into your uncertainty budget. So look for something that's operates over a reasonably wide range. Cold junction compensation is another thing to look at. A lot of the accuracy in a calibrator is stated without that, so that you need to get the accuracy of the instrument, you actually need to use an external ice bath. Well, that's a pain in the neck to walk around with an external ice bath. So you really want to find something that's, cold junction compensation built into the specifications. And that was something that when we developed our new calibrator, we spent a lot of time thinking about how do we lower the uncertainty of the cold junction compensation so you don't have to, so that we can achieve the requirements. Our goal was to be used as a portable secondary standard AMS 2750E. That's 0.2 of a degree accurate. So that device in portable, full, all uncertainty together is 0.2 of a degree. So it's pretty decent. Sorry, shameless plug, but I'm pretty proud of these new calibrators. So. Something else that we throw in these calibrators kind of useful is if you just want to do a quick statistical analysis of something, you can set the calibrator or our thermometers up to collect data, and they will compute all of these statistics. So you can actually monitor a process over a long period of time, and it'll tell you the standard deviation and the min and max. You can see all the excursions, and for a lot of things, that's all you need, and that doesn't require any special data collection. Everything's just built right into it. Tells you a little bit about the capability of your process, and we throw a 17025 cal report in with our new calibrators too.